Hello everyone. Welcome back to this lecture series on Design of RCC Structures. So far in this course, we have mainly focused on the flexural design of RCC beams, where bending moment is the dominant action. However, in real RC structure, bending does not act alone. The beams are simultaneously subjected to shear forces, especially near the supports, as well as the torsional moments, particularly in edge beams, corner beams, and beams which are supporting cantilever slabs. If shear and torsion are not properly designed, a sudden brittle failure may occur, wherein the structure may fail without warning even if flexural design is safe. Now, why this topic is important, the design of shear and torsion in the sense, the flexural failure is ductile and gradually taking place, whereas the shear and torsion failures are sudden and catastrophic. Therefore, shear and torsion design governs the safety. So, in real life examples, this shear and torsion becomes critical in edge beams, in slab beam systems, beams that are supporting cantilever balconies, beams carrying eccentric loads, even staircase beams and frame corners in buildings. A beam that is safe in bending may still fail in shear or torsion if not properly designed. With this introduction, let us proceed to the design of RCC beams subjected to combined bending, shear and torsion using the limit state method. Let us now look at the numerical problem given in the slide. We are given a rectangular RCC beam. Size is given as 300 mm by 600 mm. The factored shear force is given as 95 kN. Factored torsional moment is given as 45 kN meter. And factored bending moment has been given as 115 kN meter. The materials used are M20 concrete and Fe415 steel. So we are required to determine the reinforcement required for this beam section. And this problem represents a typical real life beam subjected to bending, shear and torsion. So such combined action is common in practice and must be handled carefully. Now we'll start with the cross section. The overall cross section has been given 300 mm by 600 mm. Let me assume a 40 mm clear cover and the beam is going to be reinforced with the 25 mm dia bars. The effective depth of the beam will be calculated as overall depth minus the clear cover minus half the diameter of the main reinforcement, which comes as 547.5 mm. That will be the effective depth. Now regarding the bending moment, we should calculate the equivalent bending moment in case of the beams which are subjected to combined flexure as well as torsion. So as per class 41.4.2, the longitudinal reinforcements will be designed to resist an equivalent bending moment, which can be computed using the formula mu plus mt, where mu is the bending moment at that cross section and mt is the torsional moment, which will be calculated using the relationship tu into 1 plus d by b divided by 1.7. So with this, the equivalent bending moment will be calculated. So here the formula has been taken, in which mu has been given 115 kilonewton meter, as well as the torsional moment is also been given 45 kilonewton meter. So overall depth of the beam is 600 mm, which is given. The width of the beam is also been given as 300. So substituting all these values, we are getting the equivalent bending moment as 195 kilonewton meter. And in this case, you can see the mu value is 115. If so, this mt value will be approximately 80 kilonewton meter as per this formula, which shows that mt is less than mu. In that case, if you are getting this condition, so the beam can be designed as a singly reinforced beam. We don't need to provide any compression reinforcement. Now the equivalent bending moment has been calculated. Then the limiting bending moment will be checked using the same relationship 0.138 FCK BD square. So substituting the value, we are getting the limiting bending moment is 248.2 kilonewton meter. Now here you can see the equivalent bending moment is less than the ultimate or the limiting bending moment. Therefore, it will be designed as an under reinforced section. Even though here I mentioned that MT, if it is less than MU, we don't need to provide any compression reinforcement. In the other case, if MT is greater than MU, it may not be coming under the under reinforced section, wherein we need to design the beam as an doubly reinforced beam. Next, we need to design the longitudinal reinforcements. So designing the longitudinal reinforcement, we'll be using the relationship which is given in annexure G1.1b. So instead of MU, we are equating it the equivalent bending moment. So substituting the values, we are getting the AST required for this beam is 1156 mm square. And the AST minimum for a beam will be 0.85 BD by Fy. Substituting, we are getting the value as 337 mm square. So in this case, the required AST is greater than the minimum AST required for this cross section of 300 by 600 mm. Now we are providing, as we already fixed, we are going to provide 25 mm dia bars. Therefore, we are providing 3 numbers of 25 mm dia bars as tension reinforcement with the AST provided as 1473 mm square. And this is what I told. Since MT is less than MU, we can provide hanger bars rather than providing the compression reinforcement. So we are providing 2 numbers of 16 mm dia bars as hanger bars. Now, as per one more class of this IS 456, as the depth of the beam, here in this case it is 600 mm. Once if the depth of the beam exceeds 450 mm, side face reinforcements has to be provided. If the depth is exceeding 450 mm, if D is greater than 450 mm, side face reinforcement has to be given. So in our case, the D is 600 mm. Therefore, it is a must that we need to provide a side face reinforcement. So how much side face reinforcement to be given is 0.05% of the area, the effective area to be provided. Now, providing 1 bar at the middle of each side, that is nothing like we have a beam. We have a beam. This is the overall depth. This is D, which is 600 mm. And since this value is exceeding 450, what we are supposed to do is one more longitudinal. Here we'll be designing the main reinforcement. We already decided this one as 3 numbers of 25 dia. And we provided 2 numbers of 16 as the hanger bars. So in addition to this one, we know that we'll be providing the stirrups. So once if you are providing the stirrups, and if the depth is exceeding 450 mm, in addition to these longitudinal bars, that is 216 mm and 325, we need to provide additional bars on the sides of the beam. That is what is called the side face reinforcement. So here in this case, we are going to provide 1 bar at the middle of each side. That is at, if this is the case in the sense, exactly half. At that particular position, we need to provide 1 reinforcement on both the faces of the beam. So the spacing of the beam bar will be calculated. That is overall depth is 600 minus 25 clear cover. This is clear cover on top, and again clear cover at the bottom, minus, that is, you can see that, let me explain with this one. So here, this is what is the clear cover. This is 25, and here also it is 25. So total is 600 minus 25 and 25 clear covers on both the top and the bottom faces, minus half the diameter. That is 25 divided by 2, and again half the diameter at the top, 16 divided by 2. That is what is the effective depth. And we are going to provide 1 bar at the middle of each side. That is why divided by 2 has been given. So we are getting that value as 264.75 mm. At this particular location only, at a depth of, that is from the base up to a depth of 264.75 mm, at this position only, we are going to provide the side face reinforcement. Now, what is the amount of reinforcement to be provided. So here area required for each bar has been given as 0.05 percentage of the area. That is 0.05 divided by 100 into width of the beam is 300, and this distance, about this distance only we are going to provide, that is 264.75. So we are getting the value as 40 mm square. So for which we are providing one bar of 12 mm diameter, which comes more than 40 mm square. So you are providing one bar, that is here 12 dia, and here also it is 12 dia. Those two are the side face reinforcements. Then going on with the transverse reinforcement. So now as per IS 456, the torsion increases the diagonal tension in the beam. Hence, the torsion is converted into an equivalent shear. That is what has been given as VE. So the equivalent shear force is given by V is equal to VU plus 1.6 TU by B, which is available in IS 456. This allows us to treat the combined shear as well as the torsion together. We can design the shear reinforcement safely. So here the torsion does not act independently. It intensifies the shear stresses in the beam. Right. So substituting the values, we already know VU, which has been given, and a TU, it's been given, the torsional moment. Substituting that value, we are getting the equivalent shear as 335 kilonewton. Now, equivalent shear stress to be calculated, that is tau VE, which is nothing like VU by BD. That is, in this case, it is equivalent, therefore VE by BD. So substituting the values, again, don't forget, effective depth we calculated as 547.5 mm. So by getting the tau VE, that is the equivalent shear stress is 2.04 Newton per mm square. And we know if tau VE is less than tau C, the concrete alone can resist the shear. In other thing, if tau VE is greater than tau C, we need to design the shear reinforcement separately. So we are providing two legs of the stirrups. And as per this class 41.4.3 of your IS 456, if you are providing two-legged closed hoop enclosing the corner longitudinal bars shall have an area of cross-section ASV, which is given by this relationship, but the total transverse reinforcement shall not be less than this condition. That is what has been given here. So ASV will be equal to this one, where SV represents the spacing of the stirrups. And B1, D1 are the effective width and the depth. And this value should not be less than this condition, tau VE minus tau C into B into SV divided by 0.87 Fi. So now we need to calculate what is B1 and D1. Let me assume I'm going to provide the stirrup as 10 mm dia bar. So in that case, B1 will be, that is effective width will be total, this is B minus 2 times the clear cover on either side. And this is what, let me show it in the figure. Here we are providing the stirrups. I didn't show the main reinforcement. Let me show with the stirrups alone. So this is what is the clear cover. That is from here to here it is 25. And from the other side also it is 25. So both the sides it is 25. And we are providing the stirrup as 10 mm dia. That is nothing like from the center to center reinforcement, that is in this direction, which is nothing like B, that is 300 minus 25 clear cover from one side, minus 25 clear cover from other side, and then minus 10 and 10. That is the diameter of the stirrups on both the sides. So you'll get the effective width as 230 mm. Similarly, the effective depth will be calculated as 600 minus here clear cover 25 and half the diameter of the top bar, that is 25 divided by 2, that is 12.5, that is this is 25 by 2. And similarly at the bottom we are provided with the 16 mm dia bars. So in that case 25 is a clear cover plus 16 by 2. So that you'll be getting the effective depth as 529.5. Now we can substitute all the values. We are getting the ASV by SV as 442 Newton per mm. So in this case, we are not considering the 0.87 Fi because both the sides 0.87 Fi is there. So we just cancelled it out. So that is why which has not been considered. We consider only TU here divided by B1 D1, here VU divided by 2.5 D1. whereas this SV has been brought to the left side in the denominator. See, we got this value. This is nothing like area of the steel required per spacing, right? So 442 Newton per mm. Now, for PT, because we already provided the reinforcement for which the percentage of the steel has been calculated as 0.9. So from table 19, for M20 grade concrete and PT of 0.9, the tau C value has been computed as 0.596 Newton per mm square. So now we can substitute that relationship, that is tau VE minus tau C into B. The denominator has not been considered because the denominator has been striked out on both the sides. So we are taking only the numerator. So this tau VE and tau C has been already calculated and B is 300 mm. Substituting that value, we are getting the value as 433.2 Newton per mm. And this value is less than 442, which has been calculated in the previous slide for the left side. Therefore, providing two-legged 10 mm dia stirrups, the spacing of the stirrups will be calculated using the same relationship, that is ASV by SV, which will be equal to TU divided by that value and SV divided by, let me show that one. This formula only we applied, that is ASV by SV is there, right? So here ASV only we calculated, that is this is 2 into pi by 4 into 10 square. SV is the only unknown in this relationship. So substituting all the values, we are getting the SV as 125 mm. That is the spacing of the vertical stirrups. Now, according to 25.5.1.7a of IS 456, the spacing of the stirrups is having some condition. That is, the spacing of the stirrup should not be greater than x1 or x1 plus y1 by 4 and 300. These SV should not be greater than any of these three conditions. So what is x1? X1 is here the center to center distance between the stirrups. That is, total width is 300 mm, 25 is the clear cover, and 5 is nothing like 10 divided by 2. That is, again, I'll be drawing here. We have the stirrups will be placed like this. Here, the thickness or the diameter of the stirrup is 10 mm, and we know the clear cover is 25. Here also it is 25. So we are supposed to calculate from center to center. This is what is your x1. That is nothing like 300 is the total width minus 25 clear cover and minus 25 clear cover on both the sides minus 10 by 2 minus 10 by 2. That is what is your x1. Now similarly, y1 has also been calculated in the similar way in the vertical direction. Total is 600 minus clear cover on both the sides minus half the diameter of the stirrup. So I'll get that one as 560 mm. So substituting that values, x1 plus y1 divided by 4 will comes 205. So we provided the spacing of the vertical stirrups as 125 in the previous slide. So now this spacing, whatever we assumed is not greater than any of these three conditions. Therefore, we can provide two-legged 10 mm dia stirrups at 125 mm centers. And this is what the reinforcement details. So wherein we can see that the overall width is 300 mm and the overall depth is 600 mm. And here the calculations being shown x1, y1, similarly d1 and b1 is also being shown. Now you can see this the maximum reinforcement, that is 25 mm dia bar, 3 numbers of 25 mm dia bar is being provided at the top, whereas the hanger bars being provided at the bottom. Why so? In the sense, the critical section for the shear and torsion will be occurring at the section which is near to the support. So once if it is near to the support, negative bending moments will be created. Therefore, the tension will be shifted from bottom to the top surface. That is the reason for providing the tension reinforcement at the top and the hanger bars being provided at the bottom. So now let us summarize this today's lecture, that is shear and torsion are critical failure modes. Torsion tends to amplify the shear stresses. IS 456 uses the concept of equivalent shear, and the design involves bending check, shear check, and the design of longitudinal as well as the transverse reinforcement. In addition, the proper detailing ensures safety, ductility as well as durability. Thank you.